Let's finish this example 7 that we were working on. This is going to be part C. We want to find the antiderivative of 3x squared times the square root of x cubed minus 2dx. A good suggestion here would be let u be the part under the radical. Let u be x cubed minus 2. Our du is then going to be 3x squared dx. This works out fantastic because that's exactly what else we have in terms of the inside of the integrand. Under the substitution, we're going to get the square root of u, swapping out my x cubed minus 2 for u, and then the 3x squared dx, that will simply give us du. This is the antiderivative of 1/2 du. We can add 1 to the power, divide by the new power, which is going to be the same thing as multiplying by 2/3, and then lastly back substitute. So we get 2/3 times x cubed minus 2 to the 3/2 plus c. Let's take a look at part D. This is one of the first problems where we kind of have the antiderivative of a proper fraction with x in both numerator and denominator. We want to find the antiderivative of negative 4x divided by 1 minus 2x squared whole thing squared dx. In terms of what to try here, one of the common suggestions in terms of doing a u substitution is sometimes you could let u be the entire denominator, but if I wanted to take the derivative of that entire denominator, that's going to require the chain rule, and it's going to get pretty involved, and it's going to give us something that's not going to look anything else like the rest of our integrand. However, if I just look at what's inside of that power again, so within the denominator, we see that we have something that's being raised to the second power. Let's let u be that thing. It's going to be 1 minus 2x squared. Notice that our du, if I take the derivative, gives us a negative 4x dx, and that's exactly what we have remaining that's going to be in the numerator. So let's do this substitution. The substitution will work. So in our denominator we have, this is now going to be u to the second power. I'll put it over top of 1 because it was in the denominator. And then the negative 4x dx, that part of it is going to substitute out for our du. This is going to be a simple or a basic elementary antiderivative in terms of u. We can first of all rewrite. Think of it as u to the negative second du. We can use our power rule, add 1 to the power. Negative 2 plus 1 is going to be negative 1. Divide by that new power, add 1 to it. So we have our plus c. To simplify this, we want to get rid of that negative exponent. So that's going to come down to the denominator. It will still be a negative fraction because we were dividing by negative 1 plus c. And now go ahead and back substitute. So our final answer is going to be negative 1 divided by 1 minus 2x squared plus c. Let's take a look at part E. We want to find the antiderivative of cosine squared x times sine x dx. We did one like this similar. Again, I find it very helpful for a lot of students to where you see that cosine squared x, rewrite it as cosine of x whole thing squared dx. For a lot of students, that kind of helps you to view it as a composition. And again, let's let u be the thing under the power. So let's let u be the cosine of x. Now our du is negative sine x dx. So I don't have everything I need right now for the du, but again, the good news is we're only off by a negative sign. I can multiply on the inside by negative 1. If I also divide on the outside by negative 1, and that will allow the substitution to work. We're going to get the negative of the antiderivative. This is now going to be u squared, and the negative sine x dx, that's going to be substituted for our du. We can now find this elementary antiderivative in terms of u, add 1 to the power, divide by the new power, plus c, and then from there back substitute. So we're going to get cosine cubed of x over 3 plus c. So negative cosine cubed x over 3 plus c. We can also look at change of variables for definite integrals. So if we have an integral of the same form that we've been working with, we can do the u substitution to find the antiderivative in the same way that we've been working. But if you think about what happens to the bounds, when we're integrating with respect to x, these original bounds are in terms of x value. So this is from x equals to a to x equals to b. When we do a change of variables, the way that it's going to affect our definite integral is as we've done before in terms of the u substitution, but the bounds are also going to change. We now need bounds that are going to be with respect to the variable u. And to find that, all you need to do is plug your bounds for x into the substitution equation to find that the new bounds are going to go from g of a to g of b. For example, let's use a change of variables to find the definite integral from 0 to 1 of x times x squared plus 1 cubed dx. So first things first, we look at the integrand. It's not a basic or it's not an elementary function whose antiderivative we recognize. We can do a substitution on this. Let's let u be the thing under the exponent. Let's let u be x squared plus 1. Then our du would be 2x dx. So we're awfully close. I have an x dx, but we need an extra 2 on the inside. We can multiply on the inside by 2 if we compensate by multiplying by a half on the outside. This should now get the substitution to fit. We're going to have 1/2 the definite integral. I'm not going to write the bounds for a moment. But on the inside, we're going to have u cubed. The 2x dx that's left on the inside, that gives us our du. And now the integration is being done with respect to u. So we need to change our bounds. Originally, if we look at our bounds, they went from x equals to 0 with the lower bound to x equals to 1. Well, now we need to convert these into u bounds. Well, remember, the substitution equation was u equal to x squared plus 1, which means that when x equals 1, u squared is going to be 1 squared plus 1, which is going to be 2. And when x equals to 0, then u is going to be 0 squared plus 1, which is going to be equal to 1. So the bounds get changed from now u equals to 1 to 2. We did our substitution. We changed the bounds. We can now finish this problem by finding this definite integral in the variable u. It's going to be 1/2 times the antiderivative of u cubed is u to the 4th over 4. And then we're going to evaluate this from 1 to 2. That is, it's going to be, I can write it probably a little more simply as what? 1/8 u to the 4th, evaluated from 1 to 2. This is going to be 1/8 times 2 to the 4th. Evaluate the antiderivative at the upper limit. Subtract the antiderivative evaluated at the lower limit. This is 1/8 times 16 minus 2, which is going to be 14 times 1/8. And 14/8 would simplify to 7/4. So the value of this definite integral is equal to 7/4. We work it out pretty much the same way we did in terms of finding the antiderivative with our u substitution, but just don't forget that whenever you do a u substitution, in addition to rewriting the function, the integrand as a function of u, you have to change your bounds into bounds that involve values of u. And that changing of the bounds is done with your substitution equation. If we let u equals x squared plus 1, that substitution relates the values of x to the values of u. Let's look at another one of these. We want to find the definite integral from 1 to 5 of x divided by the square root of 2x minus 1. It's not an elementary antiderivative. A good suggestion might be to let u be the part under the square root. Then our du would be equal to 2 dx. We look at it and we say, okay, it's a little bit of a problem because it's off by more than a constant. I don't simply have a 2 dx, I have an x dx, so that's off by more than a constant. So immediately it doesn't look like it's going to be too promising, but let's not bail on this substitution yet. We did an example of this earlier where if it doesn't exactly fit to what you're expecting it to do, try and solve for u and for du in terms of expressions for x. Excuse me, solve for x and dx in terms of expressions of u and du. If I solve the first one for x, I would add 1 divided by 2. This would give us u plus 1 over 2. This would say that dx, if I multiply both sides by a half, would be 1/2 du. And now let's see if we can get the substitution to work. I'll come back to the bounds in a moment. After all, if we can't get the u substitution to fit, it doesn't matter for changing the bounds anyway if it won't work. So the part that I was fixated on originally was we wanted to have this as the square root of u. So it's the square root of u. Everywhere we see an x, we can replace that with u plus 1 over 2. And then everywhere we see the dx, we can replace the dx with 1/2 du. And this is good, so this actually will work. We now have a integrand that's a function of u only, and the integration is being done with respect to u. So we're going to, of course, simplify what's on the inside here, but before we forget, let's go ahead and change our bounds over. Right now, the bounds are going from x equals to 1 to x equals to 5. We know that u is equal to 2x minus 1. So when x equals to 5, u is going to be 2 times 5 minus 1, which is 10 minus 1, which is 9. And then when x is equal to 1, u will be 2 times 1 minus 1, which is 2 minus 1, which is 1. So the new bounds are going to go from u equals to 1 to u equals to 9. Let's go ahead and simplify this. First of all, using the constant multiple rule, we can take the 1/2 to the outside. We have the definite integral from 1 to 9. Integration is being done with respect to u. And for this part here, if you have u plus 1 divided by 2 divided by the square root of u, that's division of fractions. Just do a keep change flip. It's going to be u plus 1 over 2 square roots of u. We can again take that extra factor of 2 out. It's like another 1 over half. 1/2 times 1/2 is 1/4. The integral from 1 to the 9th. And now we have u plus 1 over the square root of u du. The way to proceed from here is we can actually split apart the numerator. Usually whenever we're going to apply any future calculus rules with a square root, we always want to rewrite it as a fractional power. We know that that's the same thing as u to the 1/2. So we have 1/4 times the the definite integral from 1 to 9. We can split it apart as u over u to the 1/2 plus 1 over u to the 1/2 du. Simplify on the inside. We have 1/4, the antiderivative from 1 to 9, the definite integral, from 1 to 9. U divided by u to the 1/2, division by like basis, you can subtract the exponents. 1 minus 1/2 is 1/2. And then 1 over u to the 1/2 we can rewrite as u to the negative 1/2 du. From here we can now go ahead and apply our power rule to find the antiderivative. We have 1/4, which is out in front of all of this. U to the 1/2, add 1 to the power, gives us 3/2. Divide by the new power would give times 2/3 out in front. Here, if I add 1 to the to the negative 1/2, negative 1/2 plus 1 is positive 1/2. Dividing by 1/2 is the same thing as multiplying by 2. And this is evaluated from 1 to 9. We have 1/4 times, substitute in the upper limit of integration, upper bound, into the antiderivative. Subtract the antiderivative, evaluate it at the lower bound. And then from here we just have to calculate. This is going to be 1/4 times 2/3 times 9 to the 3/2 is the same thing as the square root of 9 cubed. Square root of 9 is 3. 3 cubed is 27 plus 18 minus over here 1 to the 3/2 power is 1. This is 2/3. 1 to the 1/2 power is 1. 1 times 2 is 2. So we get 1/4. 2/3 times 27. That's going to be 3 goes into 27 9 times. That's going to be what? 18 plus 18. Then we're going to have a minus 2/3 minus 2. This is 1/4 times 18 plus 18 is 36. 36 minus 2 is 34. Minus 2/3. And I'll leave the rest of this up to you. It's just a little bit of fraction work. If you take 1/4 times 34 minus 2/3, it should work out to be 25/3. So the final answer, the original antiderivative, the definite integral from 1 to 5 of x divided by the square root of 2x minus 1 dx should have a value of 25/3.